All right, now we're going to get started into analyzing sections, and what I mean by that is we are going to determine the strength of a section. Because whereas in steel or something, they only come in certain sizes and shapes, in concrete, you can make up almost anything you want. So we need to be able to calculate the capacity. So we've got to keep a couple things in mind. We're going to keep in mind our stress and strain compatibility. And what I mean by that is the stress at any point corresponds to the strain at any point. And that would be following our material properties, our stress strain curves that we determined earlier for our steel and for our concrete. Right, where were those? Right. Our steel on the left side, we assume it's elastic, perfectly plastic, and then concrete will follow that stress strain curve, although we're going to assume a stress and a strain for concrete. Also, we're going to assume that the strain distribution over the depth is linear. If we go back, give me a second to write that down. But that means if we're looking at like a cross section, right, there's the centroid. The strain distribution is going to be linear over the depth. With the top half being in compression if we're in positive bending, and the bottom half being in tension if we're in right. Tension at the bottom, compression at the top. And that varies linearly along the depth. It's not going to have anything funky. If we go back to, right, like that. See our up here, our strain is always linear. Our stress might not be linear down at the bottom, but our strain is always linear. So we're going to maintain our stress and strain compatibility, and we're also going to maintain equilibrium. sum of the forces equals 0. And our internal forces equals our external forces. Our internal forces would be like the compression force and the tension force, right? And that moment arm between them. So let's look at this cross section right here. We need now this is easy because it's a rectangle, but we need to know where the centroid is. Right, and it's, I don't know, like right there-ish. So something like, so here we have a singly reinforced beam section. Not quite at the centroid, but it'll do. Okay, we have a singly reinforced beam section. Singly reinforced because there's only tensile stress. Only tensile reinforcement on one side. Singly and we're assuming it's tensile reinforcement because it's in the bottom, and we're assuming positive bending, and tension would be in the bottom. So we are going to draw our strain profile. That's just vertical line. If we look at our strain, we said it's linear over the depth, so it goes like this. Now you notice my bottom line is not to the bottom of the section. I'm just looking from the top of the section, the most extreme compression fibers, down to the centroid of the tensile reinforcement. Because we assume, right, the bottom is in tension, the bottom half is in tension, and the top half is in compression, and we're ignoring any contribution of tension strength from the concrete. So the only thing we care about, we just assume basically that this entire assume that the bottom half of the concrete has no strength. It's in tension and it has no strength. Just assume it's entirely cracked. It's just along for the ride. So the only thing carrying tension is the AS. Right. And the only thing carrying compression, because it's a singly reinforced section, is in compression. But this is just my strain. This is horizontal strain, perpendicular to the cross section, right, in and out of the cross section. So if we're looking at, just making sure for visualization purposes, but we're really looking at, like, if this is the cross section, right, the steel, we're looking at it in like elevation view. This is the steel, and then this is the concrete. I don't know if that helped at all. It's like we're this is my cross, right? We cut our beam, this is elevation. We cut our beam right here. This is my steel reinforcement at the bottom. It's running horizontally. The rest of this is my concrete. And so the top half of the concrete is in compression, right? It's got stress on it. And my steel is in tension. Again, this is looking at it in elevation, where I have singly reinforced tensile reinforcement down at the bottom because I'm in positive bending. Concrete isn't doing anything in tension. The only thing in tension is the steel. So if I'm looking at my strain profile, this is looking at the strain profile along this line right here, right? Oh goodness. So it's linear, and I'm gonna define a couple values. First I've got the depth from the extreme compression fiber to the centroid is C, the centroid of the section. Since this is a rectangle, it would just be H over 2. And then I'm going to also define my strain values. I'm going to assume that the strain in the extreme compression fibers, so all the way up at the top, has a value of ECU, which is the ultimate tensile strain of concrete. Ultimate compressive strain, of concrete. Right. That's your Extreme compression fibers are just going to go all the way to the edge, all the way to the extreme compression fiber, extreme compressive strain, your ultimate compressive strain, which is 0.003, right? Yeah. And if I'm gonna, what we're gonna use a lot of in this class is similar triangles. So get that in your mind, right? Because I can use similar triangles to then find the strain in my steel. And we're always going to assume that the strain in my steel is greater than or equal to my yield strain of the steel. Of my reinforcing steel. What happens if I assume that my steel, or that my strain is above my yield strain? I'm going to go back to this, my stress strain. What happens if I'm above my yield strain? What's the stress in my steel if I'm above the yield strain? I hope you're all shouting, yield stress. We're going to start out with that assumption. Therefore, my stress in my steel is equal to my yield stress. And that means my section is under reinforced. Under reinforced might sound bad, like, oh, I'm under capacity, but actually it's good, because if it's under reinforced, that means I'm going to reach the full potential of my steel. It's going to reach yield, and if it reaches yield, that means I'm going to be tension controlled. Tension controlled means a ductile failure. So under reinforced is the goal. Over reinforced means you might fail in compression before you fail in tension. That means it's a brittle failure. Your concrete is going to crush. It's going to be a lot more sudden. So you want your section under reinforced. It means there's not enough steel for the not necessarily not enough, but it means that the amount of your steel isn't, well, no. It means like compared to the concrete, you're gonna fail your steel first, and you want to fail your steel first before you fail your concrete. That is what it means. So now I'm gonna look at my stress profile. I just looked at my strain. I'm gonna look at my stress. And if I look at the stress in my concrete, we talked about the Whitney stress block, right? Instead of assuming this weird parabolic stress distribution, we're going to make it look like a nice little rectangle, and it's going to have these dimensions. It's going to have a magnitude of 0.85 F prime C and a height of beta 1 C. So a magnitude of 0.85 F prime C and a height of A. The height of the stress block is A, which is equal to beta 1 times C. So beta 1 times H over 2 in this case. Beta 1 depends on your F prime C. It might be 0.85, so we might be dealing with 2.85s. You just need to remember that. And my stress in my steel, right? That's the tensile stress. Well, I just said it's my yield stress. So it's the stress in my steel, but I'm assuming it's under reinforced, so it's actually, oh, I should have put that as an F. Change that to an F down there. It's not a force, it's a stress. Just go with it. My yield stress. And finally, I want to resolve these into forces. How do I do that? I multiply the stresses. These are in PSI or KSI. I need to multiply them by an area. So I take my compression. That's my compression force. And it is equal to, and I ran out of room, the magnitude, 0.85. I'm just going to write it down at the bottom. Right? Right? I need to resolve this stress into a force. So the magnitude of it is, oops, come back a little bit. The 0.85 F prime C, right? That gives me a PSI or a KSI, depending on what values I use. The height is A, right? And multiply it by the width of the beam itself. So in this case, if you're looking here, it's into and out of the page. Right? But if you're looking at the cross section, there it is, the width of the beam, right? I'm just multiplying this stress that happens over this blue area. The height of it, I'm assuming, is beta 1C or A. So it could also be 0.85 F prime C, beta 1C B. That's the same thing. I also have a tension force. I can resolve that stress. In my steel. Remember, this compression force is in the concrete. This also happens to start with C. It's nice like that. And then my tensile force, or tension force, whatever you want to call it, which is in my steel. I have a stress, Fs or Fy. All I need to multiply it by is the area of steel, AS. So these are my two forces that I'm going to have to set equal to each other. When I'm calculating my moment capacity, I'm also going to need to know the location of these forces. You can see the tension force T happens at a distance D from the top. The compression force C happens at a distance A over 2 from the top, or beta 1 C over 2. Right, you're just taking half of that stress block to locate the centroid of the stress. So then if you're taking the moment, you just need to know the distance between the two forces, right? The moment arm. That's it. Study this page, okay? This is reinforced concrete 101, this page right here, okay? If you have questions about it, please send me an email or ask them next time we talk to each other. This is reinforced concrete, knowing the strain profile, the resulting stresses, and the internal forces. The only thing that's going to change is if we have a doubly reinforced section, or if we have a weird cross section, like with flanges or something, like a T section. But this, understanding this is Concrete 101. So take a minute, you can pause if you want to make sure you understand it. So analyzing a section. And what I mean by analyzing is we're going to calculate its capacity. or phi mn eventually. Let's say this is a given section. We already know what it looks like. Now we're just going back. We're not designing anything yet. We're just calculating its capacity. So we're given dimensions. We're given our beam width, our area of steel, our depth to our centroid of our reinforcing steel, the material capacity, the material properties, the yield stress of our steel reinforcement, and the compressive strength of the concrete. From there, the first thing we have to do is calculate beta 1, which is, right, beta 1 times C is our stress, as the depth of our stress block. Three, we're going to assume that the section is under reinforced. Again, that's not a bad thing. It means we're going to that means the strain in our steel is equal to the yield strain, which is equal to our yield stress divided by the elastic modulus of steel. And we're also going to assume that the strain in our concrete in the very, the outermost compressive fibers is equal to the ultimate compressive strain of concrete, which is 0.003. .2.2.1. Page 398. The maximum strain of the extreme compression fiber shall be equal to 0.003. Commit that to memory. Now we're going to write section equilibrium. Which means the compression force in my concrete is equal to the tensile force in my steel. I'm putting a little subscript C because once we have steel in the top in the compression zone, there'll be a C sub S. So C sub C, compression force in my concrete is equal to the tension force in my steel, which means 0.85 F prime C beta 1 CB or A equal to ASFY. And I just realized I said something incorrectly. This is not equal to h over 2. The depth to the neutral axis, if there was no steel, this would be h over 2. Neutral means, right, because this is a different material in here, with the AS in there, you're not going to have h over 2. It's probably going to be close to h over 2, but it might not be. So sorry, back to that. It's not h over 2. I said it wrong. If there was no reinforcement, it would be h over 2. But there's reinforcement, so it's not. Right, this is my A. Right, if I go back to what I was given, I know F prime C, I know the width of my beam, I know my steel, and I know my yield stress of my steel. I don't know the depth of my stress block. Of my Whitney stress block. I'm gonna write Whitney in there. So I'm going to solve for A and C, right? You can solve for A and then calculate C the other way around, which is the depth of Whitney stress block, right? And then C is just the depth to the neutral axis. They're related by that beta 1, which we already calculated, so I need to solve for equilibrium, which means I need to set equilibrium and solve for A and C. After I do that, I need to confirm my assumption that I made. I made an assumption that the section was under reinforced. Now I need to go back and check that. And how do I do that? This is where similar triangles come in, right? This was my strain profile. Right, this was my strain profile. I assumed that this value is always going to be ECU. What I need to know is ES. And I just calculated the depth of my to my neutral axis, C, and the distance, D, the distance from my extreme compression fiber to the centroid of my steel. If you go back and look at it, might look prettier here, right? ES, ECU, C, and then this whole thing is D. So how do I confirm that? I need to calculate the actual strain in my steel. Using similar triangles. Right. This triangle, they have the same, right? They have the same angle theta right there, so what can I do, right? Tangent theta, if I look at the top triangle, tangent theta is equal to opposite over adjacent, ECU, right? Opposite over adjacent, C. If I look at this angle, theta is equal to opposite, ES, over adjacent. This distance from here to here, which is D minus C. Take a moment, study that. This is a key concept, right? So I can solve for ES is equal to my ultimate strain in my concrete, 0.003 times D minus C over C. If my strain is greater than my yield strain for the steel that I'm using, great. My stress in my steel is equal to my yield stress, which is what I assumed back here, right? And it's under reinforced. If my stress, or if my strain, I'm sorry, is less than my yield strain, Fs does not equal Fy. In fact, Fs is less than Fy. We would call that over reinforced, and it's not tension controlled. that means this equation that I used right here, where I calculated my tensile force in my steel, AS times FY, now it's AS times FS. So I'm actually going to have to go back, recalculate what that is, probably do some iterations to calculate the neutral axis and the actual stress in the steel. So we'll do some examples like that. But if this happens, if you're over reinforced, but you already assumed that it was under reinforced, you're gonna actually have to go back and calculate from the beginning, and do some iterations. If you were designing it, you might say, hey, maybe I should take some steel out because I want it to be tension controlled, or reduce the amount of steel, either changing bar sizes or removing bars. The other thing we have to do, and actually you could have done this already, was calculate that you have the minimum amount of steel. Generally you do. But AS min, again, this is a tab you need. It is on page 135. 9.6.1.2, page 135. It will tell you how much steel you have. Make sure that you're, generally it's okay. But you're gonna have to make sure that you've met the minimum required steel. If you haven't, you're gonna have to increase your steel, and that might change your calculations. And finally, sorry, give me a minute. So maybe you want to do that at the beginning. But this is when you're doing designing is really why that's there. And then finally, we're going to calculate our nominal capacity, right? If I could spell it. And what that looks like is, I wonder if I can just copy this. You. Yeah. This guy goes down here. Right? If I look at my section, let's see, I also need to know my, right, I have A over 2, I'll just keep that one. And then the distance from here to here, which is D. I just need to take the moment about one of them. To get my capacity. So if I take the moment about T, my Mn is C times the distance D minus A over 2. Right, this is D minus A over 2, that's the moment arm. C was 0.85, F prime C AB times D minus A over 2. I take the moment about C. My nominal capacity is T. My tensile force minus A over 2, which is AS. Fy, assuming we're tension controlled, right? Times D minus A over 2. Obviously the bottom one has fewer variables in it, fewer chances to mess up. Although you do need to make sure, right? Right, that you're under reinforced and you've reached that yield stress. If not, that would be Fs instead of Fy. So yeah, most people use this one just because there's less numbers, less times to get it wrong. Eventually we're going to have a few factor on this. This is just the nominal capacity. But yeah, that's how you analyze a section. How am I doing on time? Oh, not too bad. So I'm going to do an example here. So we're going to ignore the compression steel, right? Because we're just going to do a singly reinforced section. So here we have a rectangular beam. We've got 4 number 8 bars. Down to the bottom, 1, 2, 3, 4. Let's get going. So let's see, my width of my beam, B. We could do it in purple if we wanted. B is 12 inches. Right. My depth from my extreme compression fiber to the tensile reinforcement, D, is 20 inches minus that 2.5 inches. Which is 17.5 inches. My area of steel, this is where we're going to have to start using our manual. I have 4 number 8 bars. So 4 times the area of a number 8. If if you go to your manual, big tab to have, or else you might start memorizing because number 8 is pretty popular. But Appendix B, page 581. Giving you a minute to get there. This is a tab you need. What's the area of a number 8? Right, not the diameter. The diameter is the first one. Like, it's a number 8, so it's 1 inch because 8 divided by 8 is 1. Because they're all in eighths up to number 8. Nominal area, 0.79 inches squared. Do not do, oh, well, let's see, the diameter of a number 8 is 1 inch, so my area of a number 8 is pi over 4 times 1 inch squared. Do not do that. Do not do that. That is not the right answer. You might think it's the right answer, but it's not. What is that value? Pi over 4, 0.785. It is 0.79 that it was what it says in the manual. Use 0.79. Do not do that. Okay. The numbers are there for a reason. It's like if you were using steel and you were like, oh, I'll just calculate my own area, not thinking about all the fillets and all that in like a W. Just don't do it, okay? Look up the number. 4 times 0.79. That gives us 3.16 inches squared. That's my area of steel. What else do I need to know? My F prime C is 4,000 psi. My yield stress of my steel is 60 ksi. And keep your units in mind. Okay? So my first thing that I need to do is, see, those are all my givens. I'm going to calculate my beta 1. Yes, my daughter shared her lovely cold. If you haven't figured that out by now, I'm super excited. Beta 1, right? On page 399, I have an F prime C of 4,000, so my beta 1 is 0.85. That's my ratio of the depth of the neutral axis to the depth of my stress block, right? So look that up. That's another tab that you need to have. It is on page 399, up at the top. My F prime C is between 2,500 and 4,000, so it's 0.85. Okay. Now what I'm going to do, I'm going to assume I'm under reinforced, so I'm going to write my section equilibrium, which is this. Right? Compression force in my concrete is equal to my tension force in my steel. I'm assuming, so I got 0.85, 0.85 F prime C So magnitude times A times B, I'll write this a little bit over, 0.85 F prime C AB is equal to Fy times my area of steel. Now solve for A because it's the only thing I don't know. So A is my tension force in my steel, ASFY, divided by 0.85 F prime CB. Now you could have also put 0.85 F prime C beta 1 CB on the left. Oh, I'll put it on the other side. Right? Because A is equal to beta 1C. And beta 1 is 0.85, so you do have two 0.85s. One of them is always 0.85, 0.85 F prime C. Beta 1 might be 0.85 quite a bit, but not always. So just remember that. You could have two 0.85s. But I'm just going to solve for the depth of my stress block. So 60 KSI, because I'm assuming that I have yielded my steel, my area of steel, 3.16 inches squared, right? 3.16 inches squared divided by 0.85. And here's F prime C, 4,000 PSI or 4 KSI. I know I told you about keeping it PSI all the time. That only matters if it's under a square root. You can change it if you want right here. Doesn't matter. And the width of my beam is 12 inches. Right? 12 inches. So 60 KSI, 4 KSI. Or you could have put 60,000 PSI and 4,000 PSI. Just keep a hold of those units. So the depth of my stress block, it's 4.65 inches. Right, that's just, we took our parabolic stress block and made it a nice little rectangle with a magnitude of 0.85 F prime C and a height of A, which we just calculated as 4.65 inches. I'm also going to, right, this is the depth of my stress block. I need to go with my depth to my neutral axis. So A equals beta 1C. So C is equal to A over beta 1 is equal to 4.65 inches divided by 0.85. Yes, there's 2.85s. There's always going to be at least one. There's often two. So 4.65 divided by 0.85 gives me a depth of 5.47 inches. So that was just to figure out the depth of my stress block and the corresponding depth to my neutral axis. So I guess it's right equilibrium. Depth of my stress block is A. Depth of my neutral axis is C. Now I'm going to verify assumption that the strain in my steel is equal to the yield strain. It's by doing my little similar triangle thing. Remember, I had my little strain profile. Where this is the value of ECU, 0.003. This is my strain in my steel. This is C. This is D. So I need to solve for ES. Alright, so strain in my steel is equal to the strain in my concrete, assuming it's 0.003, times D minus C over C. That's from back here. Right, strain in my steel is equal to strain in my concrete times D minus C over C. So strain in my steel, 0.003 times 17.5 inches. That was my D. Right? Right here. Depth to my centroid. Depth to the centroid, remember, not to the tensile steel. Not just, but I mean, it's all in a row, so it doesn't matter. But when it's not in a row, you're going to have to calculate that, or else it's given. Minus C, 5.47 inches, divided by 5.47 inches. That gives me some good news, right? 0.00, I don't know what you're going to say, 0.0066, not going to matter. What is the strain in my, what is the yield strain? So yield strain is the yield stress divided by the modulus of elasticity. So 60 KSI is the yield stress of my steel. Modulus of elasticity of steel, 29,000 KSI. Commit that to memory, okay? If you don't have it memorized already. So 60 divided by 29,000, 0.00207. This is a number that you will probably use multiple times in this class. 0.00207. see, ES 0.0066, EY 0.00207. Strain in my steel is greater than my yield strain. Yay! Therefore, it's tension controlled. Alright, if I've gone beyond my yield strain, my FS is equal to my Fy, which is what I assumed in this equation. So everything is good. Yay! I don't have to go back and do anything else. Well, I have to do one more thing. A couple more things. But I don't have to go back and recalculate all my neutral axis stuff. So let's see. Our last thing is check two more things. Check AS min first of all. So gotta go to my AS min. Again, we're on page 135. And you have to turn the page. I seriously have something that says turn the page. Is the maximum, the larger of AB. So maximum of 3 square root f prime c fy BWD or 200 over fy, right? So and that 200 is in PSI. You might want to make a little note in your manual if you want to. So that you use Fy in PSI. Right? This is your manual, write all over it, I don't care. If it makes you a better designer later, right? Helps you get the right answer. So let's see, 3 square root f prime c, so 4,000 psi, which is in psi. If you take the square root of psi, it becomes psi. It's a thing. Just accept it, okay? This is where some people get confused. Always under the square root, f prime c. Right? Under square root, use psi, square root f prime c is in psi. It comes out in psi, okay? It's a thing. So I need to use 60,000 psi instead of 60 ksi. BW is my width of my beam, which is 12 inches. And 17.5 is my D. I need 0.66 inches squared. PSI over 60,000 PSI times 12 inches times 17.5. I get to use the maximum, so let's see. AS min is 0.7 inches squared. That's the minimum amount of steel required for flexural reinforcement in non-pre-stressed, which is what we are. We're not pre-stressing. Reinforced concrete. You could probably also tell right here, right? 3 square root f prime c is 3 times the square root of 4,000 is like 190 psi, which is less than the 200 psi right here. So that's why the bottom one is going to control. So if you had a 4,500 f prime c, the top one would probably control. Right. Would be 200 divided by 3 squared. Yeah, 4444. So if you have anything over 4,444, then the top one would control. So let's see, my AS 3.16 inches squared greater than my minimum. All right. Right, AS was right here, right? My 4 number 8s. I have one more blank. Yeah. And finally, let's calculate MN. I verified that my steel has yielded, so I'm tension controlled. I have the minimum amount of steel. I have more than the minimum required. So MN is equal to AS Fy times D minus A over 2. That was all the way from back here, right? This one. AS Fy times D minus A over 2. So 3.16 inches squared times 60 KSI times 17.5 inches minus A, which was 4.65 inches. Over 2. So my nominal capacity hold on, I'll let you guys verify that. Okay. What is the units? Right? I've got, let's see, inches squared times kips per inches squared times inches. So kip inches. We probably want to know what that is in feet, so just right, times 1 foot per 12 inches. And you get 287 divided by 12. So So 240 cubic feet. And that's my nominal capacity, not reduced by a fee factor. So that's how you analyze a section. This is just, you're given a section and you have to calculate its capacity. And right now we're sticking to singly reinforced, meaning we're only taking into account the tensile reinforcement. We're ignoring up here, the steel is in compression. We're only taking into account the tensile reinforcement down at the bottom. And it's a nice rectangle. The good thing about concrete is you're gonna have nice rectangles for a lot of it. Maybe some T's, but other than that, well, I'm not gonna say that. There could be, you know, little I-beams or something, but we're gonna probably stick to some nice looking stuff. So that is how, once you are given a section, how you calculate its capacity. Okay?